Welcome to the fifth talk on machine translation. We are still not quite translating yet. We are only evaluating which of the empty outputs is better. Today we are staying within the topic, focusing on automatic methods. Empty evaluation relies on reference translations. Let's picture the situation for one particular sentence, vom Glück der träumenden Kamele. So let's assume that this box depicts all possible English sentences, or we can approximate it as all possible sequences of English words. Some of the sequences of English words are actually grammatical English sentences, and some are possible translations of this sentence. And we have seen last time that this set of understandable and grammatical translations is actually pretty large. It can be dozens or hundreds of thousands of sentences here. Now an empty system comes to this situation, and it is by principle capable of producing some set of sequences of words. The system cannot possibly produce all sequences of English words because it relies on the input sentence, and not all words are accessible from this German source. So this is all the sentences that are reachable by the empty system. And some of them are actually considered as top scoring candidates. So these are top candidates. And only one of those will then in the end win. When evaluating this particular system output, we don't have the set of all grammatical translations at hand. What we have at most is 1, 2, or perhaps 3 reference translations. And we cannot really expect that there would be an exact match possible between the top scoring candidate and one of the references. So this is the source sentence and one of the possible reference translations on the happiness of dreaming camels. And this is the system output, the happiness of dreaming camels. This is actually a very good translation, but still verbatim the two strings are different. We have to smooth the comparison somehow. So let's represent the reference translation as a set of all the words in it on the happiness of dreaming camels. And let's do the same representation also for the system output. If you then compare these sets of words, we see that they overlap to a very large extent, and only the preposition on is in the reference only and missing in the system output. For worse translations, such as this one, by the luck of the dreams of camels, we see that the set in the intersection is smaller, and there are some words that should not be in the translation, and there are some words that are missing in the translation. Here's an interesting situation. This is a sentence dreaming of the luck that camels that uses many of the words in the reference translation, but it actually says something completely different. The metric would be then confused. The metric would think that most of the words in the system output are correct, and therefore this hypothesis would get a high score. So now we have to move from something which is called position independent error rate, and that was the setup I described just before, to the BLEU score, which is a cleverer metric. And BLEU score considers not only individual words, but it also considers sequences of words, short spans from the sentence, both the reference and the hypothesis. We have seen the comparison of unigrams, the individual words that appear in the reference and in the translation, and now we add the comparison of bigrams, sequences of 2 words. So in the reference, we see pairs of words like the happiness of dreaming, dreaming camels, and camels at the end of the sentence. In the hypothesis, there are different bigrams, dreaming of the luck, and camels at the end of the sentence. It turns out that in this very strange translation, only the very last word at the end of the sentence is something that was seen in the reference translation. If we go from bigrams to trigrams, sequences of 3 words, this intersection of the reference translation and of the system output will be already empty. This is very different from the correct sentence. The translation that we liked, the happiness of dreaming camels, has the set of confirmed n-grams always pretty large. The BLEU score is based on geometric mean of n-gram precisions. Take the system B output, the bad translation, dreaming of the luck-dead camels. The BLEU score considers unigram, bigram, trigram, and 4-gram precisions. So that's the formula here. Out of 1, 2, 3, 4, 5, 6 unigrams, 4 are actually confirmed by the reference. Out of bigrams, only 1 was confirmed, and that's the camels at the end of the sentence. The whole formula is thus the geometric mean with some factor at the beginning, the brevity penalty. There are two ways how the BLEU score could be tricked. So if we have the candidate that would contain just some very reliable words, very likely words like the, that would appear in the sentence many times, the system might think that the BLEU score would give him a lot of credit for that. But the BLEU score is clever enough so that it considers only as many occurrences of a word as there were in the reference translation. So only 2 of the definite articles will be confirmed in this hypothesis. Another way of cheating is a bit more subtle. The BLEU score is a precision-based metric. That means that the denominator is based on the number of tokens that the system produced, not the number of tokens that the output expects. So if the system produces some very short sentence containing just these 2 words, the and the, it is very likely to have both of the words confirmed, and therefore the BLEU score would be very high, including the full stop at the end of the sentence. It would be 3 tokens correct of the 3 tokens produced. Obviously, we wouldn't like this short translation, so the brevity penalty is used there to penalize the system for missing so many words here at the end. Many other automatic empty metrics have been proposed, and many agree with the human judgment better than BLEU does. Yet BLEU remains one of the most widely used because of its simplicity, and also it was never surpassed in empty system optimization. So BLEU is today the standard, and it also has some standard shortcomings. I tend to distinguish between technical and fundamental problems of BLEU. First technical issue is that the absolute scores BLEU emits are not very informative. And the problem with relative comparison is that BLEU scores are not comparable across a wide range of settings. So for example, if you change the number of reference translations, the BLEU scores jump immediately. If you change the languages you're translating into, again, the BLEU scores differ wildly. And also the test set, even if it's in the same domain, can have somewhat easier sentences to translate. So BLEU scores are not even comparable across different test sets within the same domain. The main technical issue is that tokenization schemes have dramatic impact on BLEU score. So if you are evaluating something which has tags, all the tokens that are parts of the tags, the angle brackets or the slashes, could be judged as correct translations of those tokens in the reference. So obviously you actually want to remove all the tags before evaluating. The last technical issue with BLEU score is the implementation. The original paper that everybody follows is actually somewhat underspecified with respect to the brevity penalty and more reference translations. So different implementations of the very same paper can actually lead to different numbers, and the numbers are obviously not comparable afterwards. So the summary is that you should always compare only things that you have run yourself on a fixed data set in a fixed language pair and with fixed implementation of the BLEU score. And you can also never draw any conclusions from the BLEU scores alone. You always should look at the empty outputs and validate whether the improvement is indeed there. The fundamental problems of BLEU are following. It's overly sensitive to word forms. So here we have an example sentence that is being translated from English to Czech. And we have 2 system outputs here. I'm not going to read the whole sentence, that's not the point. The point is that these 2 sentences have only 1 word confirmed each. So all the rest of the sentence is not scored by BLEU at all, and the systems differ a lot in terms of quality in these unscored parts of the sentence. So large portions of empty output are actually unscored. BLEU is also overly sensitive to sequences. Let's take a look at another example. And here we have again 2 system outputs. Both systems are translating the sentence, Congress yields, US government can pump $700 billion into banks. The first system is statistical, and it therefore produces long sequences of words that are correctly validated by the reference translation. The other system produces many confirmed words, but not as long sequences. So in BLEU score, the first system actually scores much higher. The problem is, though, that these two systems differ in the unscored portions. And while the system, the statistical one, produced only nouns in this sentence and there is no main verb, the other system got the verbs right, but in different forms that the reference needed. So the second output is actually much better for the humans, but the BLEU score doesn't notice this difference. It notices only the difference in the long sequences that are better in the first sentence. It's not very surprising that the BLEU score doesn't then correlate with human judgment very often. So here in this graph, we would like to see a direct line. The higher the BLEU score, the better the manual rank of the system. And that's not the case. We see many outliers, many systems that are not very good in terms of BLEU, but they are still judged very well by humans. This is a different picture. This picture plots how the absolute value of the BLEU score relates to the correlation, and that's very interesting. The higher the BLEU score is, the better it agrees with human judgment. This observation confirms what we have said before, that BLEU score leaves large portions of the output unscored. So the more of the output is scored, the higher the BLEU score will be, and therefore the more will be actually confirmed by the reference, and therefore it is more likely to agree with the humans. So the short message here is that you should never trust BLEU under 20. Today you have heard about two automatic empty evaluation metrics, position independent error rate or PER and the BLEU score. You also know that different implementations can slightly differ in the final numbers. So why don't you implement your own PER and BLEU score in our code examiner? See the URL below. Next time we'll finally move somewhat towards empty again, and we'll be collecting data. We'll talk about data acquisition.